EDX Core Pure Sequences in Series 2 Induction. Using induction to prove results about series. Previously, we've used the formula for the sum of r squared from r equals 1 to n equals n over 6 times n plus 1 times 2n plus 1. But we haven't proved that this result is true yet. So we need to prove that it is true for the first term, n equals 1. We need to show that if it is true for an individual term, where n equals k, then it would also be true for the next term, n equals k plus 1. And then the conclusion step, that as the result is true for n equals 1, and if it was true for n equals k, it would also be true for n equals k plus 1, then it must be true for all positive integer values of n at least 1 by mathematical induction. So the first step, we need to check that this given formula is true when n equals 1. So if we look at the left hand side first, the sum of r squared starting at 1 and finishing at 1 would simply be 1 squared. It's just the first term in the pattern, which is 1. The right hand side, when n equals 1, is a 6 times 1 plus 1 times 2 lots of 1 plus 1, which would be 3. So that's 6 over 6, which is clearly 1. So we've got the same thing, the same result. Therefore, it is true for n equals 1. That's our first step of the process in place. Now the assumption step. We're going to assume that it is definitely true for n equals k. That's an assumption now. So the sum of the first k terms for r squared, the sum of the first k terms would be k over 6, k plus 1 times 2k plus 1. Then we need to consider the next term in the pattern. So now we're looking at the sum of the first k plus 1 terms. So now we're looking at the sum of r squared terms starting at 1 and finishing at k plus 1. And we need to show that this is also true for n equals k plus 1. In other words, we need to show that the sum of r squared from r equals 1 to k plus 1 could be written as k plus 1 over 6 times k plus 2 times 2 lots of k plus 1 plus 1. In other words, we've replaced all the k's with k plus 1's. So we've got to show that the formula will still hold for k plus 1. So now we're going to look at the sum of the first k plus 1 terms. So we're summing terms called r squared, starting at r equals 1 up to k plus 1. So that's the first k plus 1 terms of the pattern. That can be written as the sum of r squared from r equals 1 up to k. So we can take the first k terms of the pattern and add on the k plus 1th term. The k plus 1th term of the r squared pattern must be k plus 1 squared. There's a k plus 1th term. Now we can quote our results. We made an assumption about the sum of the first k terms of the pattern. We assume that that can be written as a 6k, k plus 1, 2k plus 1, and we need to add on k plus 1 squared. At this point, it's best to avoid expanding all the brackets and see if you can pull out a common factor instead to keep it as efficient as possible. So I'm going to pull out a 6th of k plus 1. That's a nice, neat common factor. It's also part of my solution that I'm aiming for. And let's see what we're left with. We're left with a k, 2k plus 1. And because we've pulled out a 6th of k plus 1, we are left with 6 lots of k plus 1 at the end there. Again, keep the 6k plus 1. And now simplify the square bracket. Expanding the inner brackets to see what we get. There's a 2k squared. I can see there's 1k plus another 6k, so that's 7k. And I can see at the end we've got 6 times 1 is 6. Now if I factorise 2k squared plus 7k plus 6, I get k plus 2 times 2k plus 3. Now it's pretty clear at that point that we've got it in the right form. A 6 of k plus 1 times k plus 2 times 2k plus 3, but just for extra emphasis, I'm just going to rewrite that final bracket. So 6 of k plus 1 times k plus 2, and just to make it a little bit, I'm going to write this as 2 lots of k plus 1 plus 1, just to make it clear that k has been replaced with k plus 1, and therefore it's also true for k plus 1. So there's a full method, and now we can start to look at the conclusion step. So if the conjecture is true for n equals k, then it is also true for n equals k plus 1. Since the result was true for n equals 1, it must be true for all integer values of n at least 1 by mathematical induction. In this example, a sequence has been defined by un plus 1 equals 4un minus 6, and the first term u1 is given as 3. So we've got this recurrence relationship that we need to work with. We need to prove that this could be expressed as un, the general term in the pattern un, equals 4 to the n minus 1 plus 2. So what we've got to do is take the given recurrence relationship, and we've got to prove that this is the deductive formula for the nth term of the pattern using induction. So the first thing we've got to do is to prove that this formula will give us the right answer for the first term. So u1 equals 4 to the power 1 minus 1 plus 2, which is 4 to the power 0 plus 2, which is 1 add 2, which is 3. So this deductive formula we're trying to prove gives me u1 is 3, which of course is correct. It's the given first term. Therefore it's definitely true for n equals 1. We're now going to assume that it's true for n equals k. So we can now assume that uk can be written as 4 to the k minus 1 plus 2. And we've got to show that uk plus 1, the next term in the pattern, could be written as 4 to the k plus 2. So we're looking at uk plus 1, so that's the next term in the pattern. We can quote the original recurrence relationship, so we know that uk plus 1 can be written as 4 lots of uk minus 6 from the original recurrence relationship. And now we can use our assumption step to replace uk with 4 to the k minus 1 plus 2 minus 6. So that's where we've used our assumption step. If we expand the bracket using our laws of indices, we get 4 to the k plus 8 take away 6. So we've got 4 to the k plus 2, which is the thing we were looking for. So we've just shown that uk plus 1 can be written as 4 to the k plus 2, and therefore it's also true for n equals k plus 1. So there's just a full working for you to look at. So now we can look at the conclusion step. So if the result is true for n equals k, then we've shown it would also be true for n equals k plus 1. As the result was true when n equals 1, it must be true for all integer values of n at least 1 by mathematical induction. that brings us to the end of sequencing series 2, induction.